So before we dive into the definition of the z-transform and do some examples, let's just back up a little bit and go over some preliminaries. First of all, what is z? Well, z is just a complex number. That's all it is. So z is a complex number. Typically, when working with the z-transform, we like to parameterize that complex number in the polar format like this. So we like to write it as a complex number with a magnitude of r at an angle of theta. So z is just this complex number, and we like to write it in this polar format. If we take z and raise it to the power k to create a time domain signal x of k, then what we've done is we've actually created a complex exponential signal. So while z is just a complex number, the quantity z to the k is actually a complex exponential signal. And if you do the math, take z to the k, that turns into r to the k e to the j omega k, which then, using Euler's identity, we can write in this form right here. R to the k times cosine omega k plus jr to the k sine omega k. So this is a oscillating signal. It oscillates with frequency omega, because this has frequency omega and this has frequency omega. But there's also a damping factor here. This r to the k controls how the signal's amplitude changes with time. R is what we call the damping factor. If r is greater than 1, as time gets large, the signal kind of blows up. If r's magnitude is less than 1, this is something that decays to 0 as time gets large. And the way that it oscillates is based on the angular frequency omega. So how quickly this oscillates in time is a function of omega. So what we really have here is just a complex damped cosine and sine term. If we plot these, it looks like this. So here's just an example of what this looks like. This is the signal z to the k. Here is the real part of z to the k, and here is the imaginary part z to the k. And as you can see, as time goes on, this is oscillating at a constant frequency. So both these are oscillating at the exact same frequency. And here, this example has been done for a magnitude of r less than 1. So as time goes on, the oscillations are getting smaller because the signal is being damped. So this is what the complex exponential signal z to the k looks like. It's complex, it has a real part, it has an imaginary part, and each part just looks like some damped cosine. If we did this for a different case where the magnitude of r was greater than 1, as time got large to the right, the signal would actually blow up, whereas right here it actually gets larger to the left. So depending on whether the magnitude of r is less than or greater than 1 controls whether this gets smaller as time gets large or if it kind of blows up as time gets large. So in all the math we do, we're going to be working very much with quantities z to the k. And let's talk a little bit about why we like this complex exponential signal x of k equals z to the k. So why do we like this? Well, it turns out that this signal is very special when you're talking about discrete time LTI systems. And we can see that by doing just a little math. This equation right here relates the input of a discrete time linear time invariant system to the output via convolution with the impulse response. So that's a quantity in the time domain that we're used to seeing. If we actually replace this notation with what the convolution operator means, we know that it's equal to this sum from m equals minus infinity to infinity, h of m, x of k minus m. So far we haven't done anything specific. This is just a very general relationship that we know holds for any input x of k. On this third line right here, though, I've gone ahead and assumed that the input was z to the k. So since the input is z to the k, and I need to know what x of k minus m is, I need to replace all the k's with k minus m. So that's exactly what's been done right here. All the k's in that signal have been replaced with k minus m, so it turns into z to the k minus m. Well, we know that z to the quantity k minus m can be written as z to the k times z to the negative m. And the z to the k term can be pulled outside the sum because it is just a constant term with respect to the summation, since the summation is over m. So after we do that, we now have this quantity right here times z to the k. So this is interesting. We put in z to the k, and what came out of our system was z to the k times this quantity. Well, this quantity right here, if you'll notice, it's just a number. Z is just a number. Once we sum z to the minus m times h of m over all m, we've actually summed out all of the time domain, and this is just some, in general, complex number. So the input of z to the k yielded an output of z to the k scaled by a number. That is what we call an eigenfunction of the system, because the input is exactly what came out, just scaled by a number. And that's the definition of an eigenfunction. So we like complex exponentials because complex exponentials are eigenfunctions of discrete time, linear time invariant systems. Whenever I put one into my system, I know exactly what's going to come out. It's going to come out, just possibly modified by some complex number. This quantity right here in parentheses is a very important quantity. In fact, we give it a special name. This complex number right here is what we call the transfer function of the discrete time LTI system. We describe that complex number as this. And we'll see in just a minute that this really is the definition of the Z transform we're going to use when we get into the definition. So these complex exponential quantities, e to the k, they're eigenfunctions of discrete time LTI systems, and that's why we like to represent our signals in the Z domain as linear combinations of Z to the k's, where k is some integer. And this chart just basically summarizes what we've already said in words. When you put in Z to the k, what comes out is Z to the k times this complex quantity, h of Z. So we call Z to the k an eigenfunction of the system. And the value that multiplies Z to the k is the associated eigenvalue. And this quantity h of Z is an important quantity that is essentially our impulse response transformed into the Z domain. Since h of k going into the Z domain is h of Z, and this is a complex quantity, we do very typical things that we tend to do with other complex quantities in this class. Namely, we like to break it down into the two pieces of amplitude and phase. So if h of Z is complex, we can write it as a magnitude times a phase. The magnitude is what we call the amplitude response of the system. The angle is what we call the phase response of the system. And these two quantities tell us how the input is modified. If our input is Z to the k, the amplitude of that signal will be changed by an amount, magnitude of h of Z. So all that matters is what Z are you putting into the system. Same thing with phase. If Z to the k is my input, the phase is going to be modified by the amount, angle of h of Z. So again, all that matters is what Z are you putting into the system. So the system doesn't change the frequency. All it does is change the amplitude of the frequency and the phase of the frequency. Very similar things that you've seen and heard before with respect to Fourier transforms and discrete time Fourier transforms. Alright, so this eigenfunction property and the special form of Z to the k and why we like Z to the k's gives us a hint on how now we want to define the actual Z transform.